Now, since we have learned how to encode a Turing machine in the previous video, right? We've seen how to encode a Turing machine as a binary string. We will use this concept now to think of a diagonalization language, a language called as diagonalization language. This, I think, to the best of my knowledge, is the first non-recursively enumerable language that we are covering in this course, right? So, diagonalization language is often written as LD, which basically stands for diagonalization language. This is the short form of writing diagonalization language, right? So we'll show that this is, first I'll explain what is the diagonalization language. Then I'll also prove to you why this is a non-recursively enumerable language. What does it mean? See, when I say it's a non-recursively enumerable language, it means there is no Turing machine for this problem, or there is no Turing machine to determine whether a word belongs to this language or not. Right? So let's construct it step by step. Again, the logic here is fairly dense. So please follow everything that I say very, very carefully. But once you get used to these logics, right? Or once you get used to this way of thinking, it becomes very natural. The first time around, it's slightly tricky to get our heads around it. Okay, first let me define the diagonalization language. The diagonalization language is defined as, it is a set of all the words. It is a set of all the binary words, right? What does this mean? This means Wi is a binary word, right? Such that Wi does not belong to the language accepted by machine I. Here remember, when I say machine I, what do I mean? Look at this. Here we have already discussed that for every Turing machine, I can represent a Turing machine using a binary string, which means there is which means I can interpret this binary string as a binary number base 2, which means I can think of it as a decimal number, which means I can think of a Turing machine I. Look at this. I can think of a machine I, right, corresponding to this decimal number. That's what I mean by this. Suppose if you give me a binary string I, suppose I is a number. Okay, I is an integer, right? I is an integer here, right? Given this I can convert this integer into base 2 or binary. Right? This I can interpret as a binary string. This binary string that I get, this binary string corresponds to a machine, right? That machine is what I'm calling it as MI. Similarly, this binary string can be thought of as a machine. This binary string can be thought of as a machine. This binary string can also be thought of as a word I. Right? There are two ways to interpret this binary string. One is machine I, the other is word I. Now what diagonalization language says is, it basically asks a very simple question. Does a machine, see, look at this, Wi is the same string, it is the same binary string. When you interpret it as a simple word, it is interpreted as a word. But when you interpret it as a machine, as a Turing machine, it becomes Mi. So what diagonalization language is basically saying is, given a word, given a word, given a binary word, which I can also interpret as a Turing machine, does the Turing machine not accept this word? Or if I have to write this, let me write it in English, right? So it is a set of strings. It is a set of strings which are not accepted, because doesn't belong to, right? Which are not accepted by a machine, which are not accepted by a machine, represented by the same string, represented by the same binary string, So it's a set of binary strings. Let's be more clear here. So it's a set of binary strings such that when I interpret this binary string as a machine, is this word not accepted by that machine or not? Slightly tricky. Again, thinking of diagonalization language is a non-trivial task. The people who came up with this concept, the people who actually invented the diagonalization language, are super creative. Because imagine if you are a mathematician or a computer scientist, if you are thinking about coming up with non-recursively enumerable languages, and think about coming up with this type of language. This is super creative. Again, the proof that this is non-recursively enumerable is genius. The proof of this, the proof that this is non-REL is literally genius. One of the greatest ideas, I think, in mathematical proofs that I've ever seen. So logically, it's a genius proof, to be honest, right? So first, I hope you understood what diagonalization language is. Now the next question we are going to ask, again, very important. Basically, diagonalization language is a set of binary strings. It's a set of binary strings which are not accepted by a machine that is represented by the same binary string. Right? So very simple concept here. Once you get it, that's it. Right? Now the next important question that we'll ask is LD? The important question here is LD a recursively enumerable language? So what do you mean by a recursively enumerable language? Let's ask that question also, right? Which means, suppose if a word belongs to LD, so what does this mean? So this implies if a word belongs to LD, then I must be able to construct a Turing machine that accepts this word. Then there exists a Turing machine M, that accepts every word there exists a Turing machine M such that W belongs to the language accepted by Turing machine M. Right? So see, look at this. For a recursively enumerable language, right? If a word belongs to LD, I should always halt and say, yes, this belongs. If it doesn't belong, then I might have an infinite loop or I might reject, right? Remember, for REL, there are two cases, right? If the word belongs to LD, right, I should always halt and accept. If it doesn't belong, let's assume W doesn't belong to LD, then I have two possibilities, halt and reject, or infinite loop, right? So this is what it should be. So whenever the word belongs to LD, I should always halt and accept. I need to construct a Turing machine which does this. Now what we will prove is we cannot construct such a Turing machine through a very ingenious idea called diagonalization. Okay, this language is called as diagonalization language because the proof that this language is non-recursively enumerable is done using a trick called as diagonalization. Right? So let me explain what this diagonalization concept basically is. Okay, so let's go with the flow. Okay, suppose imagine for every word, look at this, every word. So if I start writing integers here, 1, 2, 3, 4, 5, 6, I can imagine each of these integers, I can convert each of these decimal numbers into binary strings. For example, take 3. I can convert 3 into 101, right? Sorry, 1, sorry, 101 is 5. 1. I can convert 3 into 1, 2 power 0, 2 power 1. Yes. This is a binary string. This I can now interpret it as a word. This I can interpret it as W. I'll write this as W3. I can also interpret this as a Turing machine. The Turing machine will be, let's say, TM3. Right? So this you can think of this as a grid where I have each of the words 1, 2, 3, 4, 5, 6, 7. Similarly, Turing machines 1, 2, 3, 4, 5, 6, 7. So remember that whenever I say word J, if I say word 3 basically means interpret this 3 or convert this 3 into binary, whatever you get. See, 3 is in decimal, right? So convert it into binary. Whatever you get, this is word 3. This is a binary string, obviously. Similarly, whenever I say Turing machine 3, take this 3 or convert this 3 into binary, interpret that as a Turing machine representation. So I can write these Turing machines. See, look at this. Each row here corresponds to Turing machine I. Each column here corresponds to word J. Okay. Now I'll construct this table. So let's call this table as T. This whole table, diagonalization table, let's call it as T. Now each cell, if I start drawing a grid here, right? So I can start drawing a grid here like this. I can start drawing a grid like this, right? I can start drawing a grid like this. Now if you look at this, in this grid there will be, suppose if there is a cell here corresponding to the 4th row, 5th column. So what does this mean? If this value is 1, so this whole matrix is a binary matrix. Okay, you can think of this as a matrix. This is a binary matrix. So this whole matrix is a binary matrix. Now this binary matrix, this value will be equal to 1 if this implies, if any cell is 1, this implies that word 5, it implies that word 5, this column corresponds to word 5, right? This implies word 5 belongs to Turing machine 4, the language accepted by Turing machine 4. That's what 0 implies. What does, that's what 1 implies. What does 0 imply? 0 implies that, look at this, this is word 4. Word 4 does not belong to Turing machine 6, language accepted by Turing machine 6. That's what it means. So basically we are, for any row and column, look at this, for any row and column, what we are saying here is literally, is that word in that column, is that word accepted by the machine in that row. Because corresponding to every integer, I have a Turing machine. Corresponding to every integer, I can construct a binary word. Right? Very simple concept here. Now comes the interesting part. Okay, this is how we constructed this table. Again, there are multiple steps here. We have to go one by one very smoothly. So I hope you have understood how to construct this table T, or the diagonalization table, which is a binary matrix or a binary table. Now I'll define a vector called as D. This vector D is nothing but the diagonal of this matrix T. What is a diagonal? Diagonal is this, these cells, right? So first row, first column, this value. Okay. Second row, second column, this is in the diagonal. This is the diagonal. This is the diagonal. Similarly, 4 is the diagonal. So on and so forth, right? So diagonal. So this is a matrix, right? I can think of the principal diagonal here, right? So this diagonal is also a vector if you think about it. Look at this. This diagonal is also a vector. This D is a vector. The first value corresponds to whatever is there in the 1,1 cell. The second value corresponds to whatever is there in the 2,2 cell. The third value corresponds to whatever is there in the 3,3 cell. So on and so forth. The ith value here corresponds to whatever is there in the I cell. Now look at this. What does this I value represent? This I will be equal to 1. This will be equal to 1 if Wi belongs to the language of machine I or Turing machine I, right? It is 0 otherwise. 0 if Wi doesn't belong to the language accepted by my Turing machine I. That's what it means, right? Look at this. If it is third, right? Third word and third machine. Is the third word accepted by the third Turing machine? That's all. Okay, so this is what I call as my diagonal vector. Now I'll define one more vector called as D dash. D dash is complement of D. What does complement basically mean? If I have zeros here, so for example, imagine if I have 1, 0, 1, something. Okay, D dash is basically the complement of each of these values. So 1 becomes 0, 0 becomes 1. It is basically you take this vector, each of these values, each of these components of this vector or each of these cells, you complement them, right? Third becomes 0, so on and so forth now, right? So D dash is the complement of D, right? Now I'll use this. So what happens here? D dash, this value will be equal to, okay, so let me write what D dash is exactly. So D dash is also a vector, sorry, not Di, D dash. D dash is also a vector now. So if you look at the vector itself, it has indices 1, 2, so on and so forth. What does the ith index here basically mean? This ith index will be equal to 1 if, because we have complemented it, right? So exact opposite of what we have written here happens. Exact opposite. Which means this will be equal to 1 if Wi does not belong to language accepted by machine I. It will be 0 if Wi is accepted by language, it belongs to the language accepted by machine I. If you notice this, what is this? This is what we had as part of our language D, right? Or diagonalization language, if you think about it, right? So can I write it like this? D dash I equals to 1. D dash I equal to 1 implies that, or double implies. So if D dash I equals to 1, then Wi is not accepted by, is not accepted by machine I, or Wi doesn't belong to the language accepted by Mi. That's what it means, right? So now what can I do? Now can I write it as this? Okay, very interestingly. Now I can write my LD itself. Now I can write my LD itself as words wi such that d dash i equals to 1. Look at this. I can write my LD itself in terms of d dash i. Because this part, if you notice this part, what does LD say? LD says that a word wi is not accepted by the machine mi. That's what it is, right? Look, let's go back to the definition. See, what is LD? It is a set of words such that wi is not accepted by machine mi. See, if wi is not accepted by mi, we write it as wi doesn't belong to the language accepted by mi. Same story here also, right? So I can write it in this form. So whatever I have, so my d dash I, whenever my d dash I equals to 1, that implies that my wi doesn't belong to the language accepted by mi, or wi is not accepted by mi, which means I can write LD as this. Look at this, I can write my LD as this. So let me not put this curly braces here. Okay, so I can think of my Li like this. I can think of my LD using d dash i's. Right? Very interesting. Till now everything is cool. Now let's take one more step here. Okay, one more logical step here. Let's go step by step here, and I think we should be able to follow the logic from now. Okay, but these are the critical steps. So the question that we are asking here is LD a recursively enumerable language? This is the question that we started off with, right? So this is equivalent to saying, is there a Turing machine? Is there a Turing machine that accepts LD? Right? Same. This question is equivalent to this question. Now, one more thing that you have to realize here, very importantly, is every Turing machine on the earth, every Turing machine possible is there. See, look at this again, very, very importantly. Every Turing machine, so let me write this down here. Every Turing machine that is possible, corresponds to a number, corresponds to an I. Look at this. That's what we learned in the previous video, right? When we encoded a Turing machine, given any Turing machine, I can represent it as a binary string. Right? Given any Turing machine, which means given any Turing machine in the world, there is an I corresponding to that Turing machine. There is an integer corresponding to that Turing machine based on this form of logic, wherein I convert the Turing machine into a binary string. I can do this for every Turing machine. Given any Turing machine, given any binary string, I can interpret as a base 2 binary number. I can convert that into decimal, right? Which means every Turing machine corresponds to an I, or in other words, every Turing machine corresponds to a Turing machine I. See, in these columns, every Turing machine possible on the earth is there. If you go from 1 to, of course, there are infinitely many Turing machines, obviously. There are infinitely many Turing machines, but every Turing machine can be represented, is present in these rows, right? Every Turing machine. That's an important logic here. So which means, now can I say, so this is equivalent to, now, this is logically equivalent to, is there a row in, so is there a row in my table T, which is equivalent to, again, this is the most important logic, which is equal to d dash vector. Now, why am I saying this? Very important to grasp this, because a row in T corresponds to a Turing machine, right? If that Turing machine accepts LD, see, every Turing machine is represented as some row in table T, right? So I'm saying, is there a row in table T which is equal to the d dash vector? Because we have shown that LD is equal to d dash vector. We have shown that LD is same as the d dash vector, right? LD is exactly same as the d dash vector now. So I'm saying, is there a row in T which is equal to d dash vector? Again, this is a very, we could only make this logical step from here to here because we know that every Turing machine is present as a row in my table T. For every Turing machine, I have a binary encoding, and for LD itself, I can write it as d dash vector, right? So now let's argue whether this is true or not. Again, this problem we have translated into this. We have translated this problem into finding a row in T which is equal to the d dash vector. Look at this. This is my T table. Look at this. I want to find a row which is equal to my d dash vector. right? I want to find a row. Let's assume there is a row called I. So here my logic is this. Let ith row be the row in T, be the row in table T, which is equal to D dash vector. Let. We don't know whether it exists or not. Let's assume it is that. Okay, so now let's go with this. How does it look like? This TMI, this is my machine I, right? Ith row corresponds to my ith Turing machine. And now, if you look at each of these columns, now what does each of these cells tell me? Each of these cells tell me whether this Turing machine accepts word 1, this Turing machine accepts word 2, this Turing machine accepts word 3, this Turing machine accepts word I. Look at this. Now, what will this value be? Now, let's go step by step, right? Let's go very simple actually. Now, if TMI, let me write Ti as row I, right? So, what does this mean? This implies, so now what does this imply? This implies that if I imagine Ti as the ith row of this. So, let me think of this row as Ti, the ith row of table T, right? So, if I take Ti should be equal to D dash vector, right? Ti should be equal to D dash vector. So now I can write this now as Ti, the jth cell here should be equal to the jth cell of my D dash vector. So let me write this clearly instead of, okay. So this should be equal to the jth cell of this for all j equals to 1, 2, 3, so on and so forth. So what am I saying here is, look at this. This is j equals to 1, j equals to 2, j equals to 3, so on and so forth. So if this vector is equal to D dash vector, look at this, there is this vector, there is D dash vector. When are both these vectors equal? When, if component wise, if this cell is equal to this value, if this cell is equal to this value, if this is equal to this, only then your Ti, the ith row here is same as your D dash vector, right? That's what it means, right? Logically. Now, if you think about it, so I can write this now as, look at this, the jth cell of Ti. Now I can rewrite this. Look at this. How can I rewrite this? I can write this as dj complement. Because what is d dash? How did we construct d dash? Look at this. How did we construct d dash in the first place? We constructed d dash by complementing d itself. We constructed d dash. Look at this. D dash is constructed by complementing d. So if I take the jth cell of diagonal d and complement it, I'll get Tij. Right? Very simple. Now again, let's go to the next step. Now what is this? What is Tij? Look at this. What is Tij if j equals to I? So let's go for this, right? So instead of writing this, for j equals to I, right? What is Tij? Tij is nothing but sorry, you can write it as Tjj, right? So what is Tjj? Tjj, what is Tjj? Which means in the jth row, jth column. What is this? Jth row, jth column. That will belong to your diagonal. So this value will belong to your diagonal, right? Jth row, same column will obviously belong to the diagonal. What will that value be? So if you take the jth row and the jth column of your table, what will this be? This is nothing but dj. Look at this. Look at the LHS. This I can, if j equals to I, for that specific cell, if I take j equals to I, Tjj equals to dj. Because in the jth row, jth column, what is that? That's nothing but the jth cell of your diagonal. This is your diagonal, right? This element, right, which belongs to the jth row and jth column, or ith row and ith column, belongs to your diagonal, right? So this is your LHS. What is your RHS? Your RHS says dj complement. Can ever dj be equal to dj complement? Never. Because if dj is 1, dj complement is 0. If dj is 0, dj complement is 1. So they are never equal. They are never equal. Right? Which means look at the flow. Look at how I have come step by step. Which means this is a contradiction. What you arrive at here is a contradiction. What you arrive here is a contradiction. This is never true. This is incorrect. How can a binary value and its complement ever be same? They can never be same. And we have found a contradiction here. The moment you find a contradiction, you take your steps back. You go back step by step and say that this is wrong or this is not valid. And we use proof by contradiction. We are using proof by contradiction. We are using proof by contradiction and saying such an ith row does not exist. Does not exist. Such an ith row does not exist. So here we said let there be an ith row which is equal to d dash vector. Now by proof by contradiction, because we got a contradiction here, we are saying such an ith row can't exist. If such an ith row can't exist, there is no row. Again, let's go back logically, which means there is no row in T which is equal to the d dash vector. Now go back, which means there is no Turing machine that accepts LD. If there is no Turing machine that accepts LD, that implies that LD is not a recursively enumerable language, right? So LD is a non-recursively enumerable language. Look at the flow of logic here. Very, very important. Okay. And again, diagonalization is a phenomenal idea. That's why I told you, whoever came up with this language itself, they're super creative, but whoever came up with the proof is just genius. I don't know how these mathematicians came up with such an elegant proof to construct a language which is non-recursively enumerable, which means they've literally shown a problem for which you can't write a computer program, right? Literally, you can't write a computer program for this problem, right? So very, very interesting problem. And look at the flow here. We have defined a language, right? Look at the flow. I'll recap the whole flow quickly for you. We have defined a language like this, where the language consists of words which are not accepted by machines represented by the words, right? Then we constructed this whole table called the diagonalization table or table T, wherein each Turing machine, every Turing machine possible in the world is a row here, and the corresponding words are here, right? Now I took the diagonal, complemented the diagonal, right? And I've shown that this diagonal is equal to my diagonalization language. This complemented diagonal is same as my diagonalization language. Now I have asked this question. Is LD a recursively enumerable? Which means, is there a Turing machine that accepts it? Which basically means, is there a row in T which does this? Then I said, let's assume there is a row, and I proved a contradiction. And I simply proved a contradiction here. By proving this contradiction, I said, this assumption is incorrect. By proof by contradiction. Such an ith row does not exist. And going back logically, we arrive at the fact that LD is non-recursively enumerable. I think this is the first non-recursively enumerable language that we're encountering in this course till now. Very, very good problem, right? So again, such a concept. So LD itself is a very, very powerful concept because we'll use it to show that other problems in the future are also non-recursively enumerable.